Herewith, I open this academic ceremony in which Mr. Fredrik Wieland will defend his academic thesis, The Self-Assembly of Pancreatic Islets, a secret handshake that orchestrates alpha and endothelial cells. I welcome you and wish you lots of luck and success together with your parnymphs. And of course, a welcome to your supervisors as well, Dr. Lapointe and Professor van Blitterswijk. And a welcome to our opponents on site and online, whom you will meet, of course, during the discussion. And a warmly welcome to the audience here present and the people online. And having said that, before we start the opposition, I give you the opportunity to tell your family and friends what your thesis is about.
Thank you for your kind words, Prorector, and also the committee, and also the audience and family and friends sitting here. So now I'm going to present a 50-minute presentation regarding what I've done in this thesis. And it's about the self-assembly of pancreatic islets, a secret handshake that orchestrates alpha and endothelial cells. So before we start off, is that how can we advance science and medicine? So if we look at how it works nowadays in any kind of pharmaceutical settings, we have a lot of testing that we need to do. And first off is, of course, we have a disease that we want to cure. And if you look at the process how to do this, it's a long road to do. And especially if you're looking also, especially if you look in this kind of funnel structure here, you can see nicely that you start off with a lot of candidates that you want to test on a model. And this process is usually done, it could be from patient cells themselves, or it can also be a model represent this by using a single layer cells. And by doing this screening, we have a library of a lot of drugs that we can try on it. But then, of course, we need to funnel it down where we see some response in these disease models of cells that we have. And when we're coming down to maybe 10 to 20 candidates, then we move forward. And we move forward is to be called in vivo or animal models. And those models are more complex and represent more the disease in itself. And from there, we're going then hopefully next into human studies, which goes into the phases we're having here. But at the end, it's a long process, costly process, and at the end we might only have 1 or 2 candidates that comes to the pharmacy where the medical clinicians can prescribe it to the patient and thereby cure as a treatment. So how can we advance this and change this? So therefore, I already see a limitation in this funnel where we might lose a lot of candidates in the first phase. So we've been relying for many, many years and optimize it really well is when we use a single layer of cells. As I mentioned, it can be a model for disease or patients. And the advances of this is, of course, the simplicity, reproducibility, and also the accessibility of this. And that's also proven as we've been using for a long time of period. Of course, the limitation is this unnatural cell behavior, lack of cell-to-cell and cell-environment interactions, and poorly predicting the clinical outcome. And what I mean with this is that if you look at your own body, take your skin layers here on your arm, it's not just one single layer of cells, it's multiple cells that are working together. And therefore, I suggest that we should move more complex to be able to identify much better and faster those maybe more accurate candidates in the beginning. So by moving into a 3D structure, which as mentioned as the skin layers is already 3D, it gives advantage in enhanced cell behavior, improved drug testing accuracy, and more closely mimic the in vivo. What I mean with this, it's also for us, it's easier to get closer to, you can say, the animal models or even the human as ourselves. Limitation is, of course, because it's novel, it's new, and it has technical challenges and scalability issues. And therefore, there's a lot of work to need to be done. But therefore, I think we need to understand much more about cell behavior. And I was lucky to be able to start at this grant, European Research Council grant, ORCHESTRATE. ORCHESTRATE focus on building complex life through self-organization from organ to organism. It was built up by 3 major pillars. So develop a new platform for cell culture, because we need to create these 3D aggregates or 3D structures of cells together. We wanted to stimulate intrinsic self-organization capacity of cells. So if we look, for example, a simple way, sperm and egg is this. You get two cells together that merge and create what we are standing here today. And thereby create complex tissue, organs, and even organisms. And that was the main goal of this nicely grant. So I shaped it into this thesis in front of you today. How can we improve our understanding of cell interaction to better direct their behavior? So for me, when I got this question and started to think about it, we have already a nice organ in our body, the pancreas. The pancreas is built on different compartments, you can say, or sections. So you have this pancreas head at the top. In there, we have a lot of different kind of cells built into it. But it's one special one, and that's the pancreatic islets, or also called islets of the Langerhans. So as you can see nicely here on the image in the middle here, this is how it looks in your body. This white part here is the cluster of cells from the islets of Langerhans, and it plays a crucial role in regulating our blood sugar levels. So for those who don't understand this part, you might know when it's malfunctioning, it's called then a disease that's called diabetes. So why did I pick this? So as I mentioned, it's a lot of different cell types working together to balance blood sugar levels. And for us, we wanted to create pseudo-islets at the end. So the thing is that I wanted to reshape and understand this behavior, self-assembly and self-organization. So I will simplify it down and take the major cell types in there, which you might know. We have the beta cells that produce a hormone that's called insulin, and that is used then to really, for this body to take up the sugar. Then we have the opposite cell type, it's all called alpha cells. It produce another hormone that's called glucagon. This is used when we get low blood sugar levels in our body to tell the cells to release the sugar into our bloodstream. And we have the endothelial cells. Endothelial cells are there to create the blood vessels, which you all can see already on your body, on your arm. You can see we have a lot of blood vessels around there. So therefore, I created these pseudo-islets because I wanted to mimic the islets of Langerhans, but that we are able to control it and challenge the system, and thereby understand self-assembly. So how do pancreatic support cells contribute to the self-assembly and self-organization of pancreatic tissue? To answer this, in my thesis, I did multiple chapters to take you closer and go more in depth regarding this. First part, we did a nice review paper to understand about the situation in the islets of Langerhans. Then we needed to build up a setup where we can create these pseudo-islets and how we can also analyze and get information from them, what happens in the self-assembly process and self-organization. Lastly, we really went in depth and really understand this process of self-assembly. So here we can really show that we understand really the roles of the different cell types. And lastly, in chapter 5, we even found a function, a new function of cells, which is really important when you're talking about self-assembly and self-organization. And in chapter 3, the main question we had, what are the critical considerations for optimizing microscopy, imaging, and analysis of 3D cell cultures? So first off is we need to understand a system where we can create these pseudo-islets. There's a lot of systems out there, but all of them need some touch of love, I would say. What I mean with this is that you have different ways to create these pseudo-islets, but they need some optimization. So we did this, we did a lot of comparison, and we also worked because, as you can see, all of them are different. And we find a way to get the perfect and consistent way to produce the pseudo-islets. And then we also need to look in a way to be able to quantify what's happening inside, and there we need to build up a nice imaging platform, as you can say, microscopy, because I wanted to understand at single cell level what the cells are doing inside there. So therefore, in chapter 3, we underscore the benefits of optimizing an existing system for seamless integration into culture and imaging setup, enhancing efficiency and accuracy and performance. And then we went in chapter 4, what governs the self-organization of the pseudo-islets. So first thing, what we found out is that we were able to challenge this system, because I want, again, understand the organization of these 3 cell types in here. So we challenge it, the pseudo-islets, by having different starting conditions, different amount of the different cell types combined together. However, after 10 days in culture, we saw that they have a steady state they go back to. This is regulated by the cells themselves, which was really interesting for us to see. And there we start to think maybe the sizes can be an impact on this organization inside. So we did 3 different conditions of different amount of total amount of cells inside the pseudo-islet. And in this study, we saw that as larger the pseudo-islet gets, the more endothelial cells were incorporated into the pseudo-islets. So chapter 4 gives insight into the rules governing the self-organization of pseudo-islets and suggests an important role for alpha cells in their endothelialization. And as this continue, as I mentioned, I like also go in detail regarding all different cells inside there. So for us, we start to question how are they interacting, how are they communicating the cells with each other. So what we did is we quantify then, in this example here, we look at the endothelial cell in gray, and we look what kind of neighboring cell does this cell have. We did it for every cell inside the pseudo-islet, and in this case we have a 50-50 because they had 3 beta cells and 3 alpha cells around it. However, in reality, the endothelial cell had a preference towards the alpha cells, and this was even consistent over time. And also regarding the alpha cells, we saw that they were sandwiched between the 2 cell types. They had no really preference, so 50-50 in this case. And this observation made us thinking, why does this occur? And why is it this specific organization? So we thought about any transplantation, any stress these cells on the go, because in transplantation, we know that stress usually kills cells. So we thought about maybe we should look into this, what happened with the organization under stress. So in chapter 5, we got to this conclusion that incorporating both alpha and endothelial cells or GLP-1 agonists can enhance the success of transplantation of patients with type 1 diabetes. How do we come to this conclusion? So, as I mentioned, we can challenge the system. So we took out the alpha cells from the pseudo-islets. As you can see here in black, this is without the alpha cells. In white bar, we see the alpha cells presence. And we can already see, in the beginning, without no stress factors included, it's already much more stressed cells inside. And when we, of course, adding hydroperoxide, a stress factor into it, we saw that it even increased. And we know that the alpha cells can produce agonist GLP-1. And what we saw that we were able to rescue this by adding that into the beta endothelial cell pseudo-islet and thereby decrease down to levels where we see where the alpha cells are present inside to the pseudo-islet. So the final takeaway with this thesis is that we've shown that we'll be able to produce pseudo-islets consistency. We are able to image them, understand much more about the organization. We have shown how the self-assembly process is controlled by the cells. Lastly, we're able to show that also function that can be found through this 3D structure. So what do support cells provide for the islet? This finding highlights the importance of diversity and interaction of various cell types, not just those directly affected by diseased tissue or organs. Thereby focus not only on the beta cells in diabetes research. How can the role of alpha cells in pseudo-islets benefit regenerative medicine? Alpha cells are crucial for glycemic control and protecting beta cells for oxidative stress. This highlights their multi-phased rules importance in cell biology. Lastly, why should regenerative medicine make use of 3D aggregates cell cultures? Focusing on the biological details within these 3D aggregates, such as self-assembly process, cell type variation, can lead to new understanding and functional outcomes, as you saw with the alpha cells. So thereby, I would like to conclude my thesis that the thesis result suggests that we, as researchers, should go beyond 2D cell culture and introduce more complex co-cultures with multiple cell types in 3D. Thank you so much for your attention, and back to you. back to the prorector. Thank you.
Thank you for a very nice presentation. We are now going to start the opposition, and the first opponent is also the chair of the assessment committee. That's Professor Truckenmüller. He's professor of micro tissue engineering at the University of Maastricht. Professor Truckenmüller.
Thank you, Prorector. Dear candidate, please accept my congratulations for your thesis, which I very much enjoyed reading, and where I learned many new things, obviously, about pseudo-islets. You very nicely applied the pseudo-islets as a very rich playground for investigation of cell-cell and cell-matrix interactions. I would, of course, also like to extend my congratulations to the supervisor and promoter team. Now to the question discussion. I would be interested in chapter 4 on the role of alpha self in the self-assembly and endothelialization of bioengineered islets. There it says that all cell types were seeded simultaneously. Now I would be interested as a modern engineer to support the core mental shell morphology of the rodent islets rather than solely relying on the self-assembly. Have you considered also to first seed the beta cells, let them aggregate, and then seed and coat the beta cell aggregates with the alpha cells?
Okay. Dear highly esteemed opponent, thank you so much for your nice words, and also thank you for the nice question. So, the first part is that, of course, it's an interesting approach as you're suggesting, because it's also coming back to more the developing side, because it's also been shown in the discussion, chapter 4, I think I touched upon it, where you see in the 19th to 21st week, we see this already in humans when they come together. So you usually create two kind of islets which merge together. And the idea with this is, of course, that on the alpha hand side, we see more endothelial cells in there, and then you get the beta cells coming together. And yeah, we saw this afterwards, and I should give you a fast answer. Could be interesting to do. We didn't go that far, as we were looking more in the cells as they are already as a structure themselves. Thank you.
Thank you. Still on chapter 4 candidate, there on page 74, it says that pseudo-islets attain a cell type equilibrium under different seeding conditions. And then it continues, we began by altering the composition of the pseudo-islets to create 3 different seeding conditions. And then after 10 days, all 3 conditions converged on a statistically similar cell distribution regardless of their respective seeding ratios. Now, I would be interested, do you have any idea whether for the individual cell types participating in the pseudo-islets, is this mainly the consequence of cell proliferation or apoptosis? That is also, I realized, a supplementary figure 5 on time patterns of cell division and death, but it seems to me not exactly conclusive in this concern. Can you say a little bit about the potential role of proliferation, apoptosis, and...
Yeah, so thank you so much again, and it's definitely true. So that's why in supplemental figure 5, we looked into that, and it was more on the side of, you can say, the sizes where you saw a big difference in this. However, so to be honest, when I think. Sorry, I lost thought. Can you repeat just the question shortly, summarize again? Sorry.
Yeah, I can, of course. So it was mainly about if you have kind of, you anticipate, even if you have maybe not exactly experimentally looked into it, what might be the role. Are these rather proliferative effects or cell just dying to adjust the ratios that at some point it always converges?
Okay, thank you. Now I come back again. Thank you. Yeah, so what I think in that case is that, of course, you have a variation that occurs as we do with the seeding. The alpha cells that we seed proliferate over time. That's what we've seen. However, in this case of the pseudo-islets, they have rodent origins, especially the alpha and beta cells. We know that they can proliferate in that way. But I think this balance, what we see in the steady state, is that we see, I think it's because of the role of the organization. So if the size expands, we get more cells, but however, I think it's an exchange what happens, and also what we see in supplement figure 5, we don't see too much of apoptosis in there. So it's some self role in there that the cells take care of.
Thank you. And still, again, on chapter 4, going to page 76, that it says that our findings demonstrated that increasing the size of the pseudo-islets concomitantly affect the prevalence of beta and endothelial cells. Now, I would be interested, would you expect not so dissimilar effects when instead of increasing the size of the islets, for example, imposing them to a more hypoxic conditions, as might be temporarily the case after islet transplantation?
Correct. That's the way I would think also. As the sizes increase, I think also that the organization of the cells, they would say we start to need more oxygen in the core, and this can be a first step where they're trying to attract endothelial cells to build that pathway for this. And I think even if we would have expanded further, then we might have seen a different situation where we get bigger numbers inside there. Thank you.
Then I would still stay on page 76, so obviously it was an interesting page for me, that it says to determine whether pseudo-islet size affected cell type localization. We quantified whether the different cell types were found in the mantle or core. We found that increasing the pseudo-islet size also resulted in significantly greater numbers of endothelial cells in the core. Do you have any idea whether this is mainly the consequence, similarly here, of proliferation, apoptosis, or here also of migration?
Thank you so much again for the question. So what I saw through the imaging, of course, is pictures in a way you can use and look. Observation I saw was that you saw much more migration into, because if the smaller they got, you got more cell clusters. You can see the endothelial cells cluster more together as a preference, and therefore they don't get integrated. As larger they got, you saw much more building in migration of the endothelial cells into the structure, and thereby you can see the quantification of this.
And maybe I could have a last question. So generally concerning the whole thesis, I could not exactly find hints on a potential self-assembly organization of the UVEX towards some premature, maybe microvascular structures, such as corresponding networks, capillaries, and similar. Have you observed similar structures?
I should be honest, that's a big question, of course. We started off in a thesis where we looked into this and considered, okay, we're going to revolutionize this part. But I think at the end, there's a lot of extra component you need to add to this as complexity, because it might need also a little more, as you see other research out there, they give maybe hydrogel, they give kind of matrigel as extra strength for the cells to work with. And at the end is that we didn't want to head towards that, because I think also that if we extend the culture and everything, we might start to see. But as it is such a balance of different cells and also sources of cells, origin from the cells, it's also part of this calculation what we said, okay, we only look where the cells get the position, not the maturity of the endothelial cells.
Dear candidate, thank you. And dear prorector, I'm very much satisfied with the answers of the candidate. Have no further question and would give back for the further handling of the opposition to you. Thank you.
Thank you very much, Professor Drucker-Müller, for your opposition. The following opponent is also a member of your assessment committee. That's Professor Schenke Wieland. She's Professor of Medical Technologies and Regenerative Medicine in the University of Tübingen, that is in Germany. And welcome and thank you for coming all the way from Germany, albeit online. The University of Maastricht is always very happy to receive guests from abroad and outside the university. The floor is yours.
Thank you, Prorector. Dear Mr. Candidate, first of all, I would like to congratulate you to the thesis and the very important and impactful scientific work you have brought forward over the last years, pursuing here the scientific work in the lab. And so my question is focusing, the first question is focusing on chapter 2. And here you talk about the cellular and extracellular composition in the pancreas and how important these structures are for also proper function. And so my question is, what is the take-home message for you? So is the structure and the assembly of the different compositions of the cells and matrix more important or equally important to the biology?
Dear high esteem opponent, thank you so much for your kind words, and also thank you so much for a nice question. Yeah, so as you said, chapter 2 is summarizing everything in this part, and what's catch my eye a lot, specifically when I did this research, was particularly more focus on how it's organized. As for me, I think it's really interesting to look already comparison with rodent and humans. It's a big difference how the islets of Langerhans is composed. And I think this is to understand deeper why it's like this, because we know just taking beta cells cannot proliferate that much in humans compared to any rodent model where they can proliferate freely. And this is, of course, we might need to understand more. But to answer that shortly, that is mainly what I thought was really interesting, looking at the cell structure. Add to that, of course, with extracellular matrix and so on, there's also interesting components that connect more to previous component question regarding endothelial cells, because they are the one that contribute with this. And I think also when you're looking at the laminar layers and so on between the cells, it's also get interesting input into this, because this is also depending on the cell organization inside.
Thank you. Please allow me to follow up on this. So the extracellular matrix you have written in your chapter, and you already just mentioned it as well, that there are species differences. Could you also elaborate what that means in terms of the extracellular matrix?
So one example I can take is, for example, the basal membrane that's inside, where we have the laminin, where it's structured more, you can say on the rodent side, is more, if I remember correctly, I think it's the I forgot, sorry for that exactly, but it has one single layer of the basal membrane of the cells compared to a human, which has double layers, which then compose of two different kind of structures. And I think that is one of the parts that makes it interesting. Why do we see this in the human and not in the rodent, or the opposite? And then, of course, the collagen 4, where you see it's more general in all of the structures there. So you see there's a difference between species, but also we see a common part together with that.
So what implications do you see here on the use? I mean, when we look in vivo work, the majority of the models that are currently used are rodent models. So what would be here your take on that?
Yes, for me, as a take on that is that I think we should consider to understand more, as I mentioned, about how the cells behave, because you see different therapies out there, as you mentioned, we have rodent models that we're using, but some of them are using, you can say, encapsulating formats, where you're providing synthetic ECMs to give the viability higher inside there. So if we're starting to dig deeper and maybe go in towards the humans, as we see a difference in there and understand this, then we might be able to provide better safety net for the transplantations, or also if we have devices that we use then to increase the viability of the cells.
Thank you. Since you already mentioned therapies and strategies for clinical cell therapies, the current approach is very much focused on the insulin-producing beta cells. And so when I look at your work you have brought forward in your thesis, you also highlight that this is not the full story. So alpha cells come in, endothelial cells come in. If you would have to make a choice for the ideal cell therapy, what would that be and why?
So the idea would be that you take something from the patient themselves and we'll be able to differentiate, for example, stem cells in this case, to a functional mixed population of cells that we can reseed back to the cells, to the patient, sorry. Because most of the, you can say products out there that you can use, sadly the patient need also to have immunosuppressant treatment in the same time, which is also not nice for the patient. And if we were able to skip this, I think it's for them is even improvement of the therapy too, and it's no cost for their healthy in that case, or the health, sorry.
When I think about your work, you highlighted also before that the structural assembly, so the spatial distribution of the cells is crucial. So how would you be thinking about to address this in a cell therapy?
Therapy, I think the main part is, of course, you see some protocol out there, they focus on beta cells, but I would suggest skip that to heterogenic population. And it's already mentioned from last opponent, is that, of course, you see the cells are taking care of this part. So if you give them just the love and understanding, they usually can build this structure as they think is the best, in a way of balance, the dynamic part of this. So you see the self-assembly come together and give a steady state of this organization. And I think that's why just understand the cells more, and to understand what they might need is the only thing we need to do as researchers and scientists. And then trust the cells. Don't push them into something they might not like. Yeah.
So you are team cells, and they will do the right decisions for the implant. Maybe you allow me a last question before I give the word back to the prorector. You also wrote in chapter 5 about the importance of the endothelial cells and how endothelial cells interact with alpha, but also beta cells, and contribute to a fully functional composition of the pancreas. Here I was interested on your opinion. You used UVECs in your cellular approach, and UVECs are very different than pancreatic endothelial cells. So could you give me your thought about that?
It's a good point. Thank you so much. So of course, in our case, we wanted to create a model that is consistent, and that's why we took one of the most accessible endothelial cells, but of course it's still mimicking the true endothelial cells. And regarding this combination is that, of course, in the chapter 5, we focus on oxidative stress. And the interesting, you might realize when you read it through, in the beginning, we focus a lot about the endothelial cells, because in literature from chapter 2, we know that collagen 4 and so on is increasing the viability of cells. It's been proven in many, many studies. And that's why you see in the beginning, we focus on this, but we realize the alpha cells have a more important role regarding this. But regarding your question with the HUVECs, this was the decision we made to be able to create this setup of a pseudo-islet to make it more accessible.
Thank you very much. And I'm very impressed by your knowledge and by the answers, and I'm fully satisfied by this discussion. Thank you. And I give back to the prorector.
Professor Schenker-Leland, for your opposition. Now we go to the following opponent, who's also a member of the assessment committee and who's also online, and that is Dr. Manaoui, and he's a nephrologist in the University of Lille, that is in France. And thank you, Dr. Manaoui, for your presence here, albeit online. The floor is yours.
Thank you very much for the invitation. And I would like to congratulate the candidate for his amazing PhD in manuscript. I really enjoyed the architecture of the whole manuscript, and it was easy to follow the way all the science and research was built. So thank you for that, as it went deeper and deeper on the topic. My first question was actually regarding chapter 4, as the model that was used, and as you said earlier, was a convenient model because you used 3 primary cell types to build these pseudo-islets. But I was wondering if you have changed the primary cell types. Would it change the proportion of the cell types after the formation of pseudo-islets, since the ratio is so stable and steady? Is it dependent on the cell types you used?
Dearest team, thank you so much for your kind words and your nice question here in the beginning, in chapter 4. So I definitely think that it, of course, could make a difference. However, as you see, and also as you mentioned, regarding the pseudo-islet structure, we use the most common cell types out there. That's the most convenient and most researched. I believe, of course, if the origin would have been human, I think there we've seen difference in that, and also difference in the spatial organization. But I cannot say if you see this steady state and how that would behave. So that I don't have an answer to that question. But I would think definitely that the core mental organization would have been different.
Okay, thank you very much. There's a lot of work on clinical islet transplantation, and there are also works that shows after transplantation what are how the islets are stays over time, and what is the architecture and the proportion of cell types inside these islets. How do you think the proportion in the pseudo islets is the same than in the human islets that are transplanted after transplantation?
So in this case, of course, with human transplantation is, of course, we're going to more, you can say, chapter 2, where we review the structures in that way. And also chapter 4 is also mentioned in there. But I think definitely that compared to the pseudaids we're having, again, I think the core mental structure is different. That would definitely be. And with the transplantation, it's also well known that the treatment that's need to be done to isolate the islets of Langerhans is also pretty harsh, which means a lot of these endothelial cells or the vessel structures are also damaged on this process. So I think also in this case, they are not really, as we see in our healthy human being, still is going to be different. But the question is, of course, when do they come back to a different structure that maybe come closer to the human being? But that's, again, is also interesting to use this structure to understand more about this treatment and how we can maybe protect, which partially shown in chapter 5 then.
Perfect. Thank you very much for this answer. Another question is considering the proportion of different cell types after the pseudo-islet formation. I was wondering whether you had either in your research or in the literature found that there was sign of transdifferentiation from alpha to beta cells during the pseudo-islet formation process.
Yes, so thank you for the question. So this is, as I mentioned, these are original from mouse or rodent, those cells. That's why they can easily proliferate. I know from previous experience, my master, I did part of this research of seeing this switch from alpha to beta cells. And of course, that is also being well studied nowadays to understand it more. But in that case, to understand this in this part, it's not really included in this thesis stretch in that case. So I cannot say the current status and the understanding of this. But I think it's also interesting to keep in mind, as you mentioned from previous question with transplantation, maybe you can also help to give that more a strength as a switch to more beta cells inside.
Okay. Another question was more related to chapter 5. As you nicely shown that if you exposed your cells with GLP-1 receptor agonists, you decrease the level of oxidative stress, and you really pointed out in the manuscript why you chose GLP-1 receptor to target. But it's not the main function of alpha cells. So did you try other molecules, components to assess the level of oxidative stress? Did you have, for example, molecules that didn't work to decrease oxidative stress? So can you explain a bit on this topic?
Yes, exactly. So there's a lot of different antioxidants molecules out there that can be applied when you do in more clinical setting of transplantation, which you can add. But I mainly want to show in chapter 5 was more the focus on that it's known that, or partially known, it's not that much research, but the alpha cells can switch to start produce these agonists to GLP-1. And what is doing this is, of course, as mentioned with the pseudaids, you saw it was much lower stress factor. But of course, I think if you go and translate that into a clinical setting, but maybe used including the alpha cells, and might also have a start off with antioxidants, can also improve. However, this study didn't went that far in testing other molecules. It was just stopping to confirm what the cells can regulate themselves. That was the main goal of this.
Okay, thank you very much for your answers. I don't think I have more questions to you. So thank you. I'm really satisfied with this. And I return to the pro-rector for the other questions. Thank you very much.
Thank you, Dr. Manaoui, for your opposition. Now we come to the following opponent, that's Professor Balmayor. She's Professor of Experimental Orthopedics and Trauma Surgery at the University of Maastricht and working in the Department of Orthopedic, Trauma and Reconstructive Surgery in the Aachen University Hospital. Professor Balmayor, the floor is yours.
Thank you very much. I would like to start by congratulating the candidate and the promoters for a fantastic piece of work. I fully agree with you. You said before that we need to really look at three-dimensional multicellular systems to progress the field, and I think your work has done that, and it's indeed a great contribution to what we understand today for multicellular systems. And I particularly like your presentation, so I want to congratulate you for a very simple and very clear way to tell us what you did, rather complex scientific work. So let us focus on the multicellular system. This is mainly your chapter 4, right? And when you look at your book illustration, and then I just realized that actually the back part has even a more potential message, right? You have your multicellular system indeed playing together a role in an orchestrated, and that says to me that there must be a balance there that is very important for the system to work. I see cells very happy, and I see cells that are not very happy in your illustration. So I'm thinking the first question would be, can we trust on the cells to just put them together and that they will self-assemble as we need them functionally? Or do you think that this system needs tweaking and optimization of the culture conditions to make them indeed to work in that balance that we need?
Thank you so much, high esteemed opponent. Thank you for your question. Really kind words for all the presentation and the script itself. Yes, so I think we should trust them, but I think we should more looking at them, observing what they're doing. Because it could be that some cells that we're not understand fully, they might need some keys to be more happy inside there. If it's been shown in my case of chapter 5, where I show that maybe stress could be a factor why they're not behaving as they should, and by having another friend nearby as alpha cells, could in that case improve that situation. So I think this is showing a nice culture platform, as you can say, to start to understand more about the complexity. But I think for us, coming from single cell layers that's been existing for a long time as standard, this is already a trend that we should continue on, but we still need to learn so much more about this. So to answer shortly, I think they can do it, but we also need to observe well or orchestrate that part as a derogant. Yeah.
Excellent. You yourself say, since also it's stated on the thesis, there are 2 cell lines and 1 primary cell. We already see in your discussions that they are rodent-derived cells, and you say very nicely that human cells will pose a challenge. Yeah. If you will nevertheless go back and try to put more effort into your system and do this all over again, and your promoter will say, let us use human cells. How will you try to design your system then?
So to answer that question, so what I would have done, I think currently we see, the thing is that if you use real patient or donor tissue, we have a variability already in there. We know that we have some access, especially like beta cells now, that coming from origin of humans, which can be in a way used. But this is, of course, the balance of this, because if I would do it properly, I would use the platform that I built and then use human isolation, but of course on a big screening study to get understanding on multiple levels, so we don't have batch issue in that way, as this can be from the different patients. I think that's going to be the fastest and most valuable way to do this, but the most complex also included to that. And thereby also by using this method, we're also adding more cell types into it, because we have 2 other cell types that also are included, but we need to just quantify every step, and then we'll be able to understand more. If we quantify in the beginning how many cells, the different types, and what happens over time, we can learn much more faster with that method.
Great answer, I fully agree. You studied a little bit the effect, or not a little bit, actually very much in depth, the effect of the size of the pseudo-islet in this whole cell assembly and organization. Hypoxia was already discussed a little bit. What about adding stimulating factors? What about molecules?
So molecules, yeah, so especially when you go in the methods page there, I made, you can say at the end, medium mixture of all the different cell types we have in there. So of course already in there we had some VGF for the endothelial cells included, which also could be consideration to remove this to understanding more. However, we wanted to be consistent and use the same all the way through. So we know that there's more cell regulation of this, but of course this is of course that you can start play with too to understand more about what happens.
Very good, very good. The extracellular matrix was already a little bit discussed, and I'm a biomaterial person, so I'm going to pose you this question that I know that you know. Wouldn't it be valid to consider that the cells may profit from a biomaterial that provides already an extracellular matrix, or shouldn't we indeed stick to the extracellular matrix produced by the cells themselves in this cellular system?
It's a really good point there, and I, from my gut feeling, I would like to let the cells decide and do it themselves. What I think is a benefit is we're starting to use devices of encapsulation, because there is another approach of this. You're giving, of course, a structure, but you don't need to incorporate into the structure, but you're giving a protection layer. And I think you're understanding this part, that you can give the components that they don't migrate into and maybe kill the cells. It just stays on the external side, and thereby don't bother the patient too much. I think this could be the more interesting part of that, so that the device gets better integrated into the human being.
Especially for the endothelial cells, it might be indeed relevant to help them to do that vessels and other structures that they need.
Thank you so much. Yeah.
If we consider a little bit the distribution of the cells and how they assemble and how they distribute themselves into your system, you see a close proximity to alpha cells to endothelial cells, right? And you stated, and I quote, "Surely indicates an important role for the later in the process of endothelization." Which molecules will play a role there in this process of endothelization, you think?
So what is known in chapter 2 is, of course, that the beta cells can produce VGF to attract endothelial cells to start migrate, and that's could be stress, so it can be, they need more oxygen or transportation. This is the main one that I come up with mine now currently, but it's the one that's used a lot for this case. And this could be, of course, bonded in the outside to let it migrate, but that's the major one, what I would say.
Excellent. And if we consider then the beta cells in the whole distribution of the construct, do you think that the spatial distribution will be relevant for the functionality?
So it's also a big discussion in the diabetes field. It's just how do the beta cells communicate? They know that you have a membrane that usually gets some, you could say, how do you say now, electric component of it, so it gives signal to release the insulin. And if you look in rodents, it's a wave pattern to this. So you have some, you could say, lead cells that might start this interaction. So thereby, I think it's really important they are together. And we see this also in humans, the islets too, even though by eye looking at it, it looks random. However, can be a big discussion still in the scientific field, but what I believe is that the alpha cells are building a membrane between the beta cells and the endothelial cells, but it's more integrated in the human body. That's why it looks like a random pattern, but I think this structure is in there. And there you see in the rodent is more core mantle structure, and thereby the beta cells communicate and secrete outside then the insulin.
One may think, okay, it's nice to have them close to a blood vessel so that the insulin indeed get transported and so on. That is something that indeed what you say, it is relevant and it needs to be carefully looked at to correlate with the functionality of your multicellular system, right?
That's correct, yeah.
Very good. Do I have time for another short question? If we go to chapter 3, and we see a little bit amazing amount of imaging methodology development that you have done. When you use the different microwells, and this is something really very interesting, so you get in some of the microwells a more dense structures form, which we may think that is very nice, that it's what we want to have. However, it makes it very challenging, because when I want to quantify these cells and have an idea of how many cells I have, then that microwell will be more complex to use for quantifying. So how do you see?
That's a good point there. So for especially this whole chapter, we needed to test a lot of different way out there. And the thing is that if you take this pyramidal cone format, my own experience, it didn't work that well as I wanted. As you just got more spare structure, it looked like more stress. But also all of this, the head of this whole chapter was that we'd be able to culture and create the pseudo-islets in one platform in a way of culture setup, and also do the imaging inside with, you can say, staining, the process to identify the cells. At the end, later in this thesis, we even transduced them, so we had even labeled cells to work with. But all of this part is, of course, really important, because if you want to understand with more information, we need to, you can say, high throughput it. We need to go for next step, scaling. Scalability was one part I mentioned in the presentation, and therefore it's important to get that. And regarding that density of the cells, I think it's no government rule how they should look like. For us, by the eye, it looks like that, because we compare that to maybe the tissue part, but we have other cells around it that squeeze it together. So in reality, I don't know exactly how the islets looks by themselves.
Thank you very much. I'm very satisfied with the answers, and I give back the word to the project.
Thank you very much for your opposition, Professor Balmayor. Then the following opponent is also a member of the assessment committee. That's Dr. Bolognin. She's assistant professor of regenerative approaches against brain degeneration in the University of Maastricht. And today she has also accepted the role of secretary of this committee, for which I'm very grateful.
Thank you, Prorector, dear candidate. First of all, congratulations for this very nice work to you and your supervisors. A very much needed standardization work on three-dimensional cultures, because we know that the field is really moving fast, but we don't understand some of the dynamics of this self-assembly. So I really enjoyed your work. And I also liked that in different parts of your thesis you put into context your work in the field and giving references to other microtissues to see really where the field is going. So very nice work for that. And I would like to start my question referring to one of the propositions. So I would like to invite one of the Paranins to read proposition number 1. Thank you.
Proposition number 1. Three-dimensional culture systems require careful consideration of imaging and analysis workflows.
Thank you. I found quite interesting that you had as a first proposition a cautious statement toward the use of 3D culture models rather than promoting the use of 3D cell culture models. So my first question is, in your opinion, what is the compelling evidence that in your case or in general in the field 3D cultures are really more relevant than simple 2D cultures?
So, dear esteemed opponent, thank you so much for your kind words and your first question here. So, the main thing what I see with the three-dimensional culture system is that the part is that this is the platform, there's the start of creating something. And the balance of this is also, if you want to understand variability and understand much more, you need to scale it up. And there I think is already the start, how can we do this? And therefore I think not just from the 3D set, but from the 2D, we need to start with just the system of culturing first and compare that to the 2D. It still is a valuable point still to be used. However, when you're going more complex, and as I mentioned beginning of the presentation, you have this funnel of candidates that you're looking for to understand if we can have something that could maybe be a treatment. I think there we're missing a lot of those. That's why I think the 3D part is more important to focus on, because it's so many different levels in there. If you just look at toxicology, that's made big difference when there's a 3D structure in front of you or a 2D single cell layer. Because there you can say the cells die much earlier instead of the cells migrate and switch between each other to protect each other.
Mm-hmm. Nice. And indeed, when we are talking about three-dimensional microtissue, sometimes the possibility of having necrotic cores or suboptimal media and oxygen concentration inside is actually a concern. Was this ever a concern in your experimental setup?
It's a good point. Thank you so much. So as already shown in supplement figures, we saw with testing because of this question from reviewers, and we confirmed that we don't see this. I know due to the way of looking at this is microscopy, and it's optics, it's physics, and there gives a dark core when it's a larger tissue, and therefore it's a big, easy question to ask this. But already, depending how you do this, you've seen a lot of researchers out there and scientists, they are doing cutting to confirm that is not the case. And what we also most often see is that it really depends on the size of your tissue. If we're talking, you can say the ones I've been looking up to throughout this thesis is Hans Clevers and Melissa Little doing a lot of this organoid work, which they started off millimeters tissue. Nowadays they're talking about 300 micrometer tissue, and that's also big a difference because they have changed the mindset and also the time of working. And therefore I think also with our pseudo-islets, they are in the size where that is not a problem for the cells to have that. If they're getting larger, then we start to see the change, which includes one of the questions regarding endothelial cells migration.
Yeah, that's indeed very true. And also I thought it was really nice that in your system you didn't need to section the microtissues. You could image on the plate, so this gives a lot of inputs toward future high throughput or scalability. And maybe my next question is toward this direction. In terms of imaging, do you think, you were mentioning you chose different softwares and Imaris was maybe the better choice? In your case, are we really there in terms of fulfilling the high throughput requests when we are talking about these tissues? Which other implementations would you have suggested for future studies?
Yeah, we're getting closer to it, I would say, because all tissue out there is not the same. If you take a brain tissue that's easy to image, then definitely we are there. If you're getting more dense, where you have different cell types which create a more dense structure, still we have optics that are playing this part of this. Because anything that you get from the microscopes also indicate how well your analysis is going to work. So I think this is still, we need to be optimized. There's a lot of methods out there. We have clearing methods and all this that kind of approaches to, play around to really get the perfect situation. But I see, nowadays even in my work, I see much more of this getting more and more common, that you get these high throughput ways of doing it, and a lot of researchers out there and companies are relying on these studies. We're using high throughput of imaging-based 3D structures for drug screening assays.
Thank you. I have another question regarding the location of the endothelial cells. In some of your experiments, we saw that the endothelial cells were localizing mainly on the mantle rather than the core.
I think we have to leave this question for the discussion later on. If there is a reception, then we'll see that. Yeah. Okay, thank you, Dr. Bolognin, for your opposition. And Mr. Candidate, Mr. Wieland, the time appointed for the defense of your thesis has passed. And the Greek committee will now withdraw to discuss the quality of your thesis and the way you defended it, and a request that you and your company on site and online await the results of our deliberations and our return in this room. And with that, I suspend the ceremony.
Thank you.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side. 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. Better future that we go for. And even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. South side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
I reopen this academic ceremony. Mr. Wieland, the degree committee here present has assessed the quality of your thesis and the way you defended it. And in view of its positive verdict and taken into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Dr. Lapointe is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite her to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes.
Then, by the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Fredrik Carl Wieland, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. So, Fredrik, I am truly honored to be the first to congratulate you on your doctorate, and I have to say, you made it. Now, for those of you closest to Fredrik, like his family, it's so nice to see, family and friends, it's so nice to see you here today. You'll know that it was not a given that I would be saying you made it today. And I don't mean anything about the quality of Fredrik's work in his doctorate or also the quality of defense today. Fredrik, your committee referred to you as concise today in your answers, which we all know is a first. But what I refer to is this cliche of, life getting in the way. That's what I mean. And it's a funny phrase, life getting in the way, isn't it? It makes it sound like life maybe should have gotten out of your way for your PhD. And I'll admit that as a supervisor, there were some moments when I wished that maybe life had gotten a little bit out of your way and you'd had it a little bit easier at times. It would have been nice for a second if you could have focused on one thing, but when I think about where you are now and where you started, I think we have to conclude that this journey was in exactly the right way for you. And that's with all the messiness of life, poor health, death, pandemics, also getting progressively outnumbered by your children. And you found your flavor of how to bring it all together. So I remember Fredrik and I met actually on a sunny day, kind of like today. We sat down with his master supervisor, who happened to be an old friend and colleague of mine, and I liked Fredrik immediately. He was this open book, expressive in an interest for science, also actually expressive in the things he didn't want to do, which was actually really appreciated, and clearly someone with a very collaborative nature, really in his heart. And he was also willing to take a chance on me. I was a new PI at the time, really just starting a group. And Fredrik, that first encounter actually turned out to perfectly depict how our work would go together. You were always so open and willing as a PhD candidate. Sometimes this was also something we had to manage. I think it was countless times I had to tell you to please stop being so helpful to your colleagues, to focus on your own work, to put yourself first, because you always wanted to jump in when someone needed something. And sometimes you also really caught me off guard with this just incredibly positive attitude and willingness you had. We had a supervision meeting taking place on, it was July 19th, 2022. I'm sure you don't remember the exact meeting, but you'll remember the content of it because it was quite a day. You started off by informing me that your dear father's health was declining. And you also reminded me that it was the due date of your first baby. And I'm not a terrible supervisor, so of course I said, shall we cancel this meeting? I mean, you have other things to do. And you're, no, you wanted to continue, you wanted to keep going, you were going to keep your eye on your phone though, because you might be needed at home. And I think this just really shows like the type of person you are, you were and you are. And you even in that meeting asked me if maybe I would have liked a more normal PhD student, one who is not also starting a family and not distracted by all these things of life getting in the way. But no, I would not have liked a more normal PhD student. All these things make you who you are today, and everyone who has worked with you along the way will attest that you are the best colleague, collaborator, friend. You are helpful to a fault, and you performed innovative research with curiosity at all times, and also a nice love to tinker, maybe also to a fault sometimes. So with that, yeah, you're a family man on top of all of that too, and maybe life got in the way sometimes, but it was also perfect as it did. So in closing, I just want to give some thanks to everyone. So thank you for the whole Defense Committee, also our guests online for their assessment of their thesis, and also for the lovely questions today, nice high quality discussion. Thank you, Clemens, also for making this research possible. And thank you to Fredrik's friends, families, colleagues here today for supporting him on this journey, this long journey. So, and finally, thank you, Fredrik, for being a pillar of the team and for the kind of colleague that you were. So congratulations again on obtaining your doctorate. You made it. I wish you all the best for everything to come.
Thank you, Dr. Lapointe, for a beautiful laudation. Dear Dr. Wieland, also on behalf of the University of Maastricht, I would like to congratulate you. I've seen a great defense, and I hope you can celebrate it in the right way. This is one of the most important days in the scientific career. Huh? And also I congratulate, of course, your parents and your supervisors, Dr. Lapointe, Professor van Blitterswijk, and obviously your wife and children, family, friends and colleagues, online and on site. I would like to thank the members of the assessment committee for all their work, and of course the PADEL and the technical support team for making this hybrid academic ceremony possible. Then I'm about to close, and then we start the reception. I think we're about to close this ceremony. What we're going to do, let me explain that. We are going to make a picture with the two external opponents here. So we are going to ask you to leave the room already and go to the reception room, except for the photographer, of course. And then, or photographers, that's up to you. And then, when we've done that, we go to the stairs and we make another picture at the foot of the stairs. And we can include in that picture, in the second picture, also your wife and parents, whatever you want, that's up to you. Again, with a photographer. And then we go to the reception room. And then for the audience, if you think, when can we congratulate the candidate, that's very simple. You keep an eye on us. We go first and you follow. Having said that, I close this ceremony.
So, this was